Okay, thanks Professor Yo for the introduction, and thanks for everyone for joining us for this second season of the 天方夜谭 lecture series. 天方夜谭, the new horizons from dawn to dusk. This lecture series focuses on the work of outstanding female scientists in the fields of planetary and space science and astronomy, etc. Today, we are honored to kick off the new season with an exceptional speaker, just like Professor Yo introduced, Dr. Licia Ray. Dr. Ray is a senior lecturer in space and planetary physics at Lancaster University. Her research focuses on the complex interactions within gas giant systems, including the coupling between gas giant atmospheres and their local surroundings. In today's talk, titled Magnetosphere-Atmosphere Coupling at Jupiter, Dr. Ray will explore the dynamic interactions between Jupiter's atmosphere and magnetosphere, the drivers of its auroral emissions, and the impact of these interactions on Jupiter's atmospheric dynamics. So please join me in welcoming Dr. Licia Ray, and the rest is Dr. Licia Ray's time. Thank you. Yeah.
Great. Thank you very much. I know there's a camera there, but there's a whole bunch of people in the room. So for the people online, I'm going to look at the people in the room, if that's okay, because I can get some feedback to see if they've understood anything I've said by their faces. So thank you so much for the invitation. It has been fantastic to be at Hong Kong for the last two weeks, and I'll be here for the first 2 days next week too. The welcome I've had here has been wonderful. And it's a really great group. Juno and Binjang have formed some excellent teams around them that are doing some great science, and I've really enjoyed my chats. So I'm happy to have the opportunity today to talk to the people here at Hong Kong and the people online as part of the broader talk series about my favorite thing, which is magnetosphere-atmosphere coupling at Jupiter. I'm a bit biased. Jupiter is my favorite planet. It is the biggest planet. It is the brightest in auroral emissions. I think it's the most exciting for a variety of reasons. And what I really like digging into is how its atmosphere is coupled to the surrounding magnetosphere. So the first thing you might be asking is, how do we know that the atmosphere is coupled to the surrounding magnetosphere? And there's a whole bunch of things that we have measured or observed about the Jovian system that tell us that this thing is coupled. So I will try to use the mouse here so that the people online can see. So the first thing we know is that there are bright auroral emissions, and these occur across multiple wavelengths. They occur in the X-ray, the infrared, the UV, and the visible wavelengths. They are dynamic, they are highly variable, but as I'll talk about a little bit later, in contrast to Earth, they are always present. So it's not something that turns on and off with solar wind activity and with solar storms. It's always going on in the system. So here is a UV image from Hubble. Oh God, it's not going to show on one. All right, here we go. I'm going to see how much I can well coordinate things. So there's a UV image from Hubble. There's an H3 plus image from Juno. This is an artist's interpretation of heating, auroral heating, that is now affecting the entire atmosphere of the planet. So we know that this connection between the planet and its surroundings can affect the global atmosphere. We know that there's something going on because when we look at plasma profiles in the magnetosphere, so far away from the planet, the behavior of the plasma in terms of its rotation velocity doesn't act as you might expect it to. So you would expect there to be some deviation, and we'll get to why, but the plasma profiles show these interesting bits of co-rotation, which tells us that there is a connection. And we can see evidence of particles precipitating into the atmosphere. So we know that things are going from the magnetosphere into the atmosphere. And the first detection that these regions were coupled was by radio emissions. So I didn't mention radio emissions, and I won't mention them much, but we have indications in that wavelength as well. So all of these things can be taken together, and we can start to think about the question of how are Jupiter's auroras generated. And because ultimately aurora is a signature of a coupling between a planet and its surroundings, that's a nice place to start. So I know a lot of people in the room and online might not study Jupiter. So a basic fact sheet about Jupiter. Jupiter is the largest planet. It has 95 moons, and it is huge. 1 Jovian radii is 10 Earth radii. Its atmosphere reflects solar composition. So it's not anything like our atmosphere at Earth. It's hydrogen, helium, some hydrocarbons. And the ionosphere, the ionized portion of the atmosphere, which can drive electrical currents and coupled to its surroundings, is composed primarily of protons and H3 plus particles. It's not like Earth, it's a very fast rotator. So instead of our long 24-hour day, which feels quite luxurious, at Jupiter, it's a 9-hour and 55-minute day. So it doesn't leave much time for sleep or work. You're just rushing all the time. And the magnetic field is quite strong. So the magnetic moment is 20,000 times stronger than Earth's, and it is an offset tilted dipole. The most prominent feature on Jupiter is the Great Red Spot. And if you want, just for size scale, you can fit Earth right inside of it. So we're looking at something that's much bigger than anything we're used to talking about. And it doesn't sit in a vacuum. So we're not going to talk about the planetary surface here. We'll talk a little bit about the moons. We have the atmospheres, but Jupiter itself is embedded in interplanetary space. And the sun is a very active body. It has a wind that comes out from it, and that wind carries with it protons and electrons and other ions from the sun. It moves rapidly outwards through interplanetary space, and it interacts with the bodies. So hold on, let me enable captions. Okay, so I'll play this again. All right, if that didn't work, whoever requested them, feel free to ask for the captions again, and I'll try to hit the button again. So this solar wind goes out through the solar system. It goes past Mercury, Venus, Earth, where we are, where it causes our nice, bright, highly dynamic and variable aurora that responds very much to solar activity and coronal mass ejections. Mars, I know some people in here are doing Mars and Nook. Sorry, I'm not going to do too much. I'm not zapping rocks, but I'll zap your planet with a solar wind. We have the asteroid belt, which some of the work that you can do on the asteroid belt is similar to some of the work that's being done on lunar return samples, looking at solar wind impact on lunar rocks. And then finally, it gets to Jupiter. But Jupiter isn't just sitting out in space unprotected, it has its own magnetic field. And so the solar wind interacts with this magnetic field. The magnetic field has a force associated with it that acts to repel the solar wind or present an obstacle to the solar wind. And this creates Jupiter's magnetosphere. So I'm sure some of you have seen a slide like this from Jean-Noir or his group, or Binjing and his group. But this is Jupiter's magnetosphere, and it is the largest object in the solar system. So Jupiter sits here at the center. The thing in yellow is the Io plasmatorus, and that is formed by the innermost moon Io, which sits well inside the magnetosphere at 6 planetary radii. Earth's magnetosphere itself fits, most of it fits inside the planet. So we're talking about a structure that's far bigger than anything we have locally. So Io is sitting here at 6 planetary radii. The magnetosphere itself extends out, and its location can vary, and it can vary as a function of solar wind pressure, or as Enhao, who's sitting in the room, has shown in many of his papers, it can vary as a function of mass loading rate, so the amount of material that Io is ejecting into the system that then is ionized and transported. So this boundary here, this nose of the magnetosphere, can be from 60 planetary radii out to 100, 120. If that were Earth, based on the system physics at Earth, that boundary is at 10 planetary radii. So this tells us that not only, at Earth it's at 10. If it was an Earth-like system at Jupiter, it would sit at 40 planetary radii. So the fact that it's not sitting at 40, and it's sitting at 60, 80, 90, all the way out to 100, 120, tells you that there's a lot going on in the system. And just for those of you who enjoy going out in the night sky, and Jupiter is up right now, as is Venus and Mars and Saturn, If we could somehow light up the magnetosphere, send a bunch of fireworks out to celebrate the upcoming new year, it would be huge. It would be bigger than anything else. So what I'm going to do in this talk is I'm going to go through different aspects of the Jovian system and how they are connected, and hopefully demonstrate that there's a lot going on. So the very first thing I'm going to talk about is Io and the Io plasma torus. So I like to call Io the moon that could. It's the innermost Galilean moon. There are 4 Galilean moons: Io, Europa, Ganymede, and Callisto. Io sits at 6 planetary radii, as I've mentioned, and it is subject to huge, huge tidal forces. Io, Europa, and Ganymede are in an orbital resonance. That means for every 4 orbits that Io does, Europa does exactly 2, and Ganymede does exactly 1. Over time, this has had the effect of slightly perturbing Io's orbit, so it's not perfectly circular. And that little bit of ellipticity, because of the proximity of Io to Jupiter, means that Io is constantly being squished and forced. And so the inside of it is liquid, right? It's not all the way into the inside, but this whole thing is flexing. That generates a lot of heat, that frictional heating, that leads to plumes, it removes water, and it drives volcanic activity. Io is the most volcanically active body in the solar system. So for the geologists in the room, there is stuff outside of the local system, and we could send robots to Io, but they'd probably very quickly be covered in material. So we'll have to come up with robots with umbrellas or something good like that. So here is Palan, 5 months apart, and you can see the activity. We've also caught sight of some of the geysers on the limb. Juno has imaged Io in the infrared, and you can see very clearly these hot spots on the surface where there is activity. And my favorite for Io is this movie from New Horizons as it flew by, where we really got to see Tavashtar going crazy and these plumes erupting and descending down. Io ejects approximately 1 ton per second into the local system. Exactly how the material goes from here into the local environment is still a bit of a mystery. There's a lot of processes that need to happen, and there's a lot of exploration going in on that area. But once it does get into the local system, there are a lot of things that can happen. So the chemistry is sulfur dioxide based. It's not a pleasant place. It's a stinky place. And if you look at this, these neutrals, as they are, they can form a neutral torus, which is shown in the bottom here with the sodium atoms. And neutrals are fine and they're interesting to some, but they don't interact with magnetic fields. So they don't really interact with the planet. And so we need to do something else. These neutrals need to be ionized, and there are a number of processes that can do that. There is photoionization, although at Jupiter that doesn't play a huge role, and that is because there's so much material that the photons aren't really penetrating into the Io neutral torus as much as it should. There is electron impact ionization, so high energy electron beams present in the system. Those can ionize neutrals. And that works. But the most efficient way of ionizing neutrals is through charge exchange interactions. So charge exchange is when a neutral that is orbiting around Jupiter at the Keplerian speed interacts with an already existent ion in the system, and that will be moving around with this 9-hour, 55-minute periodicity. So that is in contrast to the 57-hour orbit of Io. The interaction occurs and you end up with a slowly moving ion that was previously a neutral and a fast moving neutral that was previously an ion. Does anybody have a question? Okay. But I don't mind. I'm not messing with it. All right. And we can see the ions, the ion plasma torus that is generated here. So we can image these tori. They appear in UV wavelengths. They appear in X-ray wavelengths. And they are going to do quite a bit for the system. So let's go here. All right, so what exactly do these tori have to do with the coupling between the moon and the atmosphere, or sorry, the magnetosphere and atmosphere? So the moons themselves can generate an auroral signature. They present an obstacle to the system. It's conducting, but the atmosphere around it is presenting an even bigger obstacle. This, as the magnetic field is orbiting, the magnetic field is rotating with the planet underneath it. And as it passes over the moon, this can generate Alfvén waves, so magnetic perturbations that travel along the planetary magnetic field. They accelerate particles and they descend into the atmosphere. There is a localized spot of emission that is related to these moons. At Io, it's the Io footprint, which is here on the screen. It's this bright area. There are also footprints for Europa and for Ganymede. Europa is thought to have a slight potential source. It would be water-based chemistry, not sulfur dioxide-based chemistry. Ganymede has its own magnetic field that presents an obstacle to the atmosphere. So the moons themselves will present a spot, an obstacle that creates a spot. This wake of emission here, this tail that follows Io, that tail is generated by the need to accelerate and pick up newly generated or slowed down stagnant ions that exist behind Io in terms of the magnetic field. So the magnetic field is moving from this direction across Io and forward. So the material behind Io here needs to be sped up to speed once it's ionized. That generates this wake. So that's the first thing that Io does in terms of generating magnetic signatures. The second thing is the main auroral emission. And this is something that is still under discussion and under debate, exactly what processes, specific processes are generating Jupiter's main auroral emission. But I think to the 0th order, mass transport and currents associated with that are playing a large role. So what happens to mass from Io? You'll remember Io is sitting, excuse me, at 6 planetary radii. It's well inside the magnetosphere, and it's putting all of this material out. So 1,000 kilograms per second, say. Half of it in the charge exchange process is lost. When they become fast neutrals, it leaves the system, but the other half remains. It's not going to stay at Io forever. It has to move somehow outwards through the system. So it's transported radially outwards. And again, this is where Binzheng and Enhao are doing some fantastic work with their MHD simulations, looking at how the mass goes through. It might be through radial interchange. There may be fingers of plasma flowing out through the system. It takes a while for the mass to get from Io out to 10 planetary radii, where Europa is. Once it gets out past that, it goes quickly out. So once it gets to 10, it starts moving out farther. It moves out in radius. Centrifugal forces play a huge role because of this rapidly spinning disk. Now, what should happen as material moves outwards? So we're all familiar with conservation of angular momentum. So if you take material and it moves out, it should slow down. So if it slows down, it'll be moving slower. It would be presented, if you're looking in a frame rotating with the planet, it would be bending back. But it's ionized. If ionized material moves backwards, it drags a magnetic field with it. The plasma in the field are frozen together. So where one goes, the other must get. So here's my figure skater for what the plasma is doing, but that's okay. So it's moving it and dragging it backwards. Well, once you drag material backwards on this field, you've introduced a kink to the magnetic field and some new configuration. That then is related to currents. Electrical currents are going to flow from the planet down along the field, the magnetic field. They'll flow radially outwards in the magnetosphere through the plasma, eventually closing in the planet, going back to the planet rather, and closing through the atmosphere. In this region where the purple is, we can measure what the plasma rotation is. And if it were slowing, then you would be seeing something where the plasma rotation Juno, can you assist me, please?
Yes, sure.
Okay, great. Do you want to be the pointer on the
Yeah.
computer or do you want to be the pointer up here? Okay,
I'm
so
good.
if it were slowing down, then the plasma would be doing something like this, right? That's what you would expect from conservation of angular momentum. We measure the plasma, it's not doing that. So this is rigid co-rotation, rotating 9 hours and 55 minutes, like a solid body with the planet. 80% co-rotation, 60% co-rotation. The fact that this is rigidly co-rotating tells us that something like this current system has to exist, and I'll go through that in a second. So that is telling us that they're coupled. Thank you so much. And that shows up on both. You're a genius. All right, this will go easier because Jean-Noir is a genius. Thank you. All right, so we have this plasma moving outwards. The disruption of the magnetic field generates or leads to a current. Here's your electrical current in yellow. And that current flows radially outwards before going back along the field and closing in the atmosphere. This part of the circuit here, that will have a Lorentz force, a J cross B force associated with it. And that will act to accelerate the plasma in the direction of co-rotation, remove that bend back from the field if it can, and keep the plasma co-rotating like we see in the data. So the data tells us that this is happening. And the aurora is the observational counterpart at the atmosphere. Now, currents on their own don't generate aurora. There has to be particle acceleration going on. And I'll touch on that a little bit later. That part of it still remains a mystery. But this will create a nice omnipresent auroral emission. So the aurora at Jupiter, because it's related to this transport of mass from 6 RJ outwards, is always on. I don't think there's, it can change, it can expand, it can brighten, it can contract a bit, but it's always there. I've never seen an auroral image from Jupiter where there isn't any aurora at all. And we know that it's being driven by an internal process because this movie is from Hubble. So if you're sitting at your computer screen, pretend you're Hubble. So you'll be in the Earth direction, Sun-Earth direction from Jupiter. If you're sitting in the room, again, pretend that you're Hubble. So you are sitting in the Sun-Earth direction. The fact that this auroral structure is rotating with the planet underneath you means that it's an internal process. It's not an external process like Earth's aurora. If we want, we can look at that in a different frame. So here, we've taken the auroral images from Hubble. Denis Gredant made this movie. So Denis is somebody that Jean-Noir has worked closely with in the past as well. All of these are now projected onto the planetary grid. So this is a fixed planetary longitude. The reason why this terminator is moving is because Jupiter's rotating as Hubble views it. So sometimes it's there, sometimes it's not. And you can see that this structure remains largely fixed in planetary longitude coordinates. This spot here, that is Io. And it appears to move retrograde because the planet is spinning faster, right? So the planet has a shorter period of rotation than Io's orbital period. And then you have Ganymede creeps in up here near the edge. So we have this internal emission. It appears, like I said, in a vast range of wavelengths. So we have X-ray, infrared, visible. There are radio signatures, UV signatures. This again is the infrared image from Juno. And it's a huge amount of energy and angular momentum that is transferred between Jupiter and the surrounding plasma. So if you want a number, it's 10 to the 13 to 10 to the 14 watts is the best estimate. And if you want something to relate that to, it's 10,000 to 100,000 nuclear power plants. So this is a significant interaction, and it's happening in our local solar system. So I'm going to move on a bit to the atmosphere now. So the atmosphere is heated from this interaction. All these things are coupled, right? These electrical currents are flowing through the atmosphere, out along the field, through the plasma in the distant magnetosphere and back. And that is going to have an effect. There's a couple reasons why the atmosphere is heated. And so this is H3+ measurements from ground-based observatories. I don't remember this image at the moment. But the two things are particle precipitation which can heat the local atmosphere. It has a bigger role in ionizing the underlying atmosphere or exciting the atmosphere and then generating these auroras. And we can measure these auroral particles with Juno and see them coming in and find their energies. And you can see these auroral emissions marked out in the northern and southern hemispheres. But that's not the main source of heating for the atmosphere. The main source of heating for the atmosphere is Joule heating. So these electrical currents that are closing through the atmosphere up here have the effect of exerting an anti-corrotational force on the underlying thermosphere that couples to the middle magnetosphere. And they also will present some Joule heating. So there is a current, there's an electric field, and this presents a source of Joule heating or frictional heating in the atmosphere. And then once that heat is deposited in the atmosphere, it can be transported, although I'll talk a little bit about the transport more in a bit. So we know that these global currents are going to close through the atmosphere. And this is some work that a student of mine did a few years ago, where he looked at all of the magnetometer data in the magnetosphere from the first missions to Jupiter in the 70s, all the way out to midway through 2018 with Juno. And he calculated what the current densities are, what the electrical currents are running through Jupiter's magnetosphere. And he found that there are radial currents present in the system, which we know because we have those J cross B forces. Although something's wrong with this figure, sorry, because that and that match. So I'll show a different one of this in a bit. Azimuthal current densities and field aligned. These ones here are the ones that are associated with that bright auroral emission that I talked about. And in terms of them being a heat source, I know I discussed this, but here they're threading through the thermosphere. These are the current closure currents. They act in a co-rotational way, and we can model the deposition of energy and the temperature increases in the atmosphere. Now, there is a big question in Jupiter science, and that is, why is Jupiter's atmosphere so hot? The thermospheric temperatures that we measure are hundreds of Kelvin larger than you would expect from solar EUV heating alone. So this is a big outstanding question. Auroral energy has to play a role in this. I can't think of anything else that is going to provide global heating constantly to the atmosphere. The big mystery is, how do we get the heat from heating the atmosphere here away from the poles? Because a lot of the models suggest that it moves to the poles, and there are some ideas for that. And we can look at the wind transport and circulation patterns, but there's more work to be done. So we know that the energy is deposited by the poles. We could see that in the H3+ emissions. And we now have evidence that it reaches lower latitudes. So there have been some models that have been done on this, and I will show this one here. This is one that says, all right, so the models that have the heating getting trapped in the poles, those all assume a steady state system. So you have the magnetosphere, you have the coupling of the magnetosphere to the atmosphere. You can model the currents, you can feed them into the atmosphere, you can look at the energy deposition in the atmosphere, the Joule heating, the ion drag, the energy circulation, but you keep your magnetosphere fixed. And when you do that, under those assumptions, your energy is trapped. If you somehow pulse or compress the system, so you can do that with, in this study, it was a solar wind compression, but maybe in the future we'll use some of in-house MHD work that shows that you can stretch the magnetodisk with mass loading. If you introduce a time varying change, then that breaks the forcing of energy up to the poles. So this work was done by a colleague of mine, Jeff Yates, and the middle magnetosphere here, which maps to the auroral current region, the co-rotation enforcement current region. When you start pulsing the system and adjusting it, you can start to get heat moving down towards the equator in these waves. So this model was published, the model results were published in 2014. 7 years later, they were able to find some evidence that this is happening. Now, I would love more evidence. I would love to have more data points closer together. But they have images of two auroral events, one in April 2016, one in January 2017. And what they find is they find a different temperature profile as a function of latitude moving down the planet, which is suggesting that the lower latitudes have been warmed. They were able to connect this back to solar wind changes by looking at the solar wind data, propagating it out, and saying that there had been a compression event that happened before this observation. And that they're speculating that is what is driving this change. Now, what we really need is we need some way to look at this and have a constant monitor in real time. So a constant solar wind monitor and a constant temperature monitor. That's okay. It is some sort of evidence. So how exactly is auroral energy circulated through the atmosphere? That is still a huge outstanding question that we really need to understand.
So Licia,
Yes.
is that a one-dimensional model of the high upper atmosphere?
This one.
The other one, yeah.
This is this is a 2.5D.
Yeah, so I have a question about trapping the energy, because we have these Earth aurora space weather stuff, right? You can deposit these in the aurora, you heat the thermosphere, they initiate all these TADs and you travel with Coriolis effect.
Yeah.
It's about 3 hours. So the polar region gets heated and equatorial region heats up every 3 hours. So to Jupiter, I think it could be even faster because it rotates faster.
The strong Coriolis forces associated with the rotation really are just shunting things forward. So we're not seeing any leakage to equatorial regions, but we
Not
could
the formal measurements.
not well, the measurements are far and few between. So this is the best set of measurements that there's any heat leaking out. We know that the atmospheric temperature in this part of the disk is hundreds of Kelvin larger than it should be. And here it's 500-600 Kelvin more than it should be. So there has to be some leaking of the heat. But the models, the Coriolis forces associated with models always are shoving it up because of the rapid rotation. So I'm not sure what in Earth, but the only thing I can think of what's different in the Earth model is the rotation. Is it the slower rotation? Yeah.
Actually, this is exactly what the battery piece was about.
Fantastic.
So if you have like general simulation models, you actually get different kinds of rotation regimes. And the interesting thing is that actually, like if you can actually small models and big the big planets, there are certain depending on, for example, how far they rotate and like what kind of temperature difference you have between pole and equator. Actually, like very big planets can also be similar like small ones. And the special thing about Jupiter is because it rotates so fast, you actually get like multiple heavy suns. So basically, like the lines that you see, like all these like bands,
Yeah.
exactly like the thing. And what I would expect, I did like models that did not have such a deep atmosphere because they did terrestrial planets.
Well, this is very much the upper atmosphere for these
Yeah.
models. It's the high region. So the Hadley cells are
The upper atmosphere operates in different ways. One you describe as a lower atmosphere.
Yeah.
Those does not apply to the upper
Because
atmosphere.
like otherwise, I would expect that it would actually the heat transfer would be more difficult.
Oh,
because it would have, like,
density is much lower.
Yeah.
So the density is always magnitudes lower. So all the human energies constantly, everything's very low.
It's something that needs more work. And I'm gonna move on though. So we can happily discuss in a bit. All right, I'm now going to just talk a little bit about Juno and talk about some of the things that Juno has discovered, found, that people have been able to do with the Juno measurements and some of the big questions that I still have about the system. All right, so Juno has been finding a lot more mysteries. So the temperature crisis that's called the giant planet energy crisis has been something that numerous grants have been written on for decades. And we obviously want to solve it, although then you restrict your ability to write more grants based on the giant planet energy crisis. But obviously that's a joke. Nobody's laughing, which makes me worry. All right, so enter Juno. Juno is still in orbit around Jupiter. It arrived at Jupiter in 2016, and it is unique in terms of Juno orbiters and Juno missions. And this is because it is highly elliptical. It skims the atmosphere. It measures particles and magnetic fields and images the aurora. Other missions did that too. But the benefit of its orbit in this highly elliptical polar orbit means we have had unprecedented access to auroral currents, to imaging the aurora and removing biases introduced by looking at Jupiter from Hubble, which is our greatest source of information to date. It has allowed us to explore these regions of the magnetosphere, which previously had not been explored. And it's really, I think, opened up the field for us. So if we go back to this image here, so this is the work that my student Chris did years ago, and I had a master's student, Andrew, who kind of looked into it and updated it. Here are your radial currents. Sorry, here are your field-aligned currents in the system. This yellow line here is a statistical location of an Alfvén radius. And the physical meaning of the Alfvén radius is the boundary where information can easily be communicated to the planet inside of here, because the radial velocity of any plasma is smaller than the Alfvén velocity. That's kind of a typical communication velocity along the magnetic field. Outside of this, plasma is moving too far out radially to be able to communicate back with the planet. I'm showing the statistical version, but again, using Bin Zheng's model and using Jean-Noir's student. So sorry, Yan, if you're on the line. We have also looked at this in numerical simulations, and we find that it's very dynamic, but if you average over large timescales, this kind of structure is borne out in the global models as well. What this means is that at Jupiter, in the midnight sector, the dawn sector of the tail, things going on here are not going to be easily coupled to the planet. But if you're in the noon or the dusk, the afternoon sector of the magnetosphere, these areas, you can still couple to the planet, albeit weakly. And when we look at auroral structures, that is something that I think is supported by the aurora. If you look at Jupiter's orbits, the nice thing that Jupiter is allowing us to do is it's allowing us to explore this region here where you're going to have highly dynamic variability and not much planetary control over what's going on in the magnetosphere. And these are just the regular mission. It's been extended. They have now done orbits to here, and they'll get around to here by the end. So they're also going to be going into this region where you are completely coupled, albeit weakly. And I think that by comparing data and behavior, system behavior in this region, and then in this region, we're going to be able to learn an awful lot about the magnetosphere. All right, so in terms of mysteries and exciting things, Juno is the first mission that has been able to measure particle acceleration above the aurora. So there were so many studies done about this over the years, including part of my thesis. And we tended, before Juno arrived, to apply lessons from Earth. So there have been many satellites at Earth. FAST is the most famous one, I think, that measured particle acceleration above the atmosphere. And what we knew from Earth is that particles, auroral particles at Earth, are accelerated into the atmosphere most of the time by electric fields that are oriented parallel to the magnetic field. And that's the structure that we see over our brightest aurora. Any particles that are accelerated by waves, by this disturbance in the magnetic field, those are associated with kind of the most boring diffuse aurora or polar aurora. And we thought that that's what we would see at Jupiter as well. Well, Juno arrived, and it flew, and it skimmed along these field lines, and it's seen something very different. So here we have a lot of things here. This is the pitch angle of the electrons. So this tells you if they're going down into the planet or up away from the planet, or just kind of hanging out, spinning around the field like this. We have the electron energy. So this is the energy of the particles. And what you see here is you see this structure here, which is very intense over a very narrow range of energies. And that's telling you that all the particles went through the same acceleration process. So that's saying that there's an electric field somewhere above the spacecraft that's making all the particles have the same energy. Then you see structures like this, where you have a whole bunch of electrons with increased intensity over a range of energies. And the fact that it's over a range of energies, that's telling you that there's waves going on, because when you're slowly accelerating plasma constantly along a magnetic field, you get this signature. So we expected everything to be like this. And instead, we see this mix. So that tells you that the physical processes driving Jupiter's aurora are quite different, which I guess makes sense, right? You have this internal mechanism driving it. Why won't the acceleration be different as well? So one big question is, why is the particle acceleration so different from that at Earth? Okay, you have the internal driver, you have the motion of the plasma going around, but what's making it wavy all the time instead of electric field driven? And I know Juno has a lot of ideas on that and has been working a lot with multiple data sets, which I'll get to in a second.
So Licia,
Yes.
why would you call this different? Because the invert V and the broadband auroras are also measured at Earth.
It is, but they're not measured in the same places. So Jupiter's
Oh,
most
the same
so Jupiter's most discrete aurora is associated with broadband acceleration. Earth's most discrete aurora is associated with quasi-static. And then the diffuse aurora at Earth is associated with broadband. So the fact that the strongest, most energetic aurora is associated with the wave-driven process instead of something that's kind of constant above the atmosphere, shunting particles down, is something that was completely unexpected.
Okay.
And the other thing that was really unexpected about this too is just the close proximity of these regions. So because of how Juno's going through like this, what you're seeing is a spatial feature. What we really want are more spacecraft, so we can say if it's a spatial or a temporal feature. It would be great if somebody sent 3 Junos out to Jupiter, and then you could really, or even 4 would be better, and you can really start to pinpoint this. But seeing this morphing, is this telling us that there's something that's the broadband is creating the initial density cavity, then that's turning into the static one? Maybe this is something that we can't observe at Earth because it doesn't happen. So that's why it's different.
I see. Okay.
All right. So the other thing was, we expected to see oxygen and sulfur in the plasma disk in the equatorial plane of the magnetosphere. These are heavy ions, and they're going to be centrifugally confined by this rapid rotation. When we can see that this is the ioplasma torus, but they're kind of confined here. And modeling had been done that looked at, this is Vlasov modeling that looked at the potential structure along the field, the density distribution of plasma along the field. And the modeling had said, well, really, these heavy ions should be confined. Well, Juno shows up, and this here, this gold box here, is the region of this simulation here that I did long enough ago that maybe I am Jean-Noir's mother. It makes me feel old. I'm not. Sorry, let it be clear. So here's the Io torus in the northern hemisphere observations and in the southern hemisphere observations. These top panels in each of these are heavy ions. And what we're seeing is a higher number of intense heavy ions outside the plasma sheet and at high latitudes. They're all being measured up here. They're not being measured down here in this equatorial region than expected. So how are these heavy ions getting up the field? What is pushing them up? Are they more energetic? Is something happening to give them more parallel energy? I think that's a big question. And there has been some work doing this, and this is a study that Jean-Noir did that was published in Science, I think, in 2021. And this was looking at wave accelerated ions. So looking at ion cyclotron waves as a mode. I believe it was ion cyclotron waves. As a way to get these heavy ions up. Now, this is out in the distant magnetosphere because this is associated with X-ray aurora and polar things. But perhaps this is something that we need to look at closer to the planet and then modify our modeling to address. One thing that has been nice is that Juno has found auroral currents. So you have these currents driven by the radial transport, and you can predict some sort of a deviation in the magnetic field associated with them. Now, the magnitude isn't necessarily perfect, but we are seeing deviations in the bend back of the field at polar latitudes that are low, that are associated with large-scale upward or downward current systems. And of course, there's variations and striations in them. But that's encouraging that maybe we understand the most basic level of the auroral drivers properly. But one thing is that they have different magnitudes. And is that related to the ionosphere? Is that related to the magnetic field structure? Because Jupiter's magnetic field is highly distorted in the northern hemisphere. I think hemispheric asymmetries and how they affect the planet plasma connection is an area where we can do a lot of work. And then another surprise, and perhaps the biggest one, is that the atmosphere is leaking, and it's not leaking where we thought it would. So at Earth, there is a wind that flows out of the poles. And it's really flowing out of the poles, right? So inside Earth's auroral oval, this isn't Earth, this is Jupiter, but up at the top region. At Jupiter, they're seeing all of this outflow, and that's not in the polar region. That's in between the aurora associated with the moon, Io, and the main emission. So there are, you know, this is something that I think needs to be better explored. One thing that it could be is it could be that as those flux tubes are pulled out and diffusing out, moving out from the system, that creates a pressure gradient at high latitudes as you're stretching that. And maybe that's siphoning material out, but I think it needs to be better understood and better modeled. We have an outflow model at Lancaster, but at the moment it's buggy, so we are working on fixing it. So what drives this ionospheric outflow? So there's a lot of data right now with Jupiter, and I think one thing that we're lacking, well, there's two things that we're lacking. One is more observations and kind of system scale observations, but I'll talk about that in the next slide. And the other thing is models. So when you do your studies in geology, or if you do Earth magnetosphere or something like that, you're spoiled for choice, I think, with a lot of numerical models and backing. Although maybe that's not true in geology, and so you can tell me I'm wrong. At Jupiter, we're pretty far behind. There's been a lot of energy put into getting the data, and we have all these single spacecraft observations. But the system's huge, right? It's 100 planetary radii out on the day side, on the planet sunline, and then you're going out, and we have a puny little spacecraft. I mean, it's not even like the size of a dust mite in comparison with the system. And it's zipping around and it's taking these data points, and it's great. I don't want people to say that you shouldn't send missions to Jupiter. You 100% should send lots of missions to Jupiter, but send an extra satellite so you can get two sets of measurements and then correlate them. But we also need to have these models, because then you can start to interpret the spacecraft's observations in a bit of a different manner. You have no way with a single spacecraft to say, is it a spatial change? Is it a temporal change? And really, you need more than two to do that as well. So there's a few different sets of models. I'm not going to go into them in great detail because I know we're out of time. But there's waves, electric fields, atmosphere, and auroral currents. I tend to work in this area here with outflow models, GCM models, and current models. There's magnetosphere focus models, and I think that HKU is really fortunate. I really do think you have the best model at the moment that is looking at Jupiter. It is absolutely brilliant, and it's offered so much insight into the community. And it's really benefited because you also have an expert in data analysis over multiple wave bands, data types, aurora, magnetic fields, and plasma. So you have a dream team here for the science, and I hope you're exploiting it as much as you can. So what do I think? Well, I think we need to get some more modeling work done, and I'm on sabbatical now. So I'm hoping to work a lot more with my atmosphere models and do some science instead of teach and do admin. The aurora is generated by the coupling of the planet and the plasma. The moons play a huge role. Some of the exact mechanisms are still not known. There are complex interactions everywhere, and the models and the data are really equally important. It's not have one, forget the other. We will have more data in the future. Juno is in its extended mission until I think it's the end of next year, end of this year, beginning of next year. JWST is giving us some great information, but that's a little bit deeper in the atmosphere than is ideal for me. JUICE and Europa Clipper will be up there soon. But we need innovative measurements to push the field forward. So a lot of these things are, it's great, and I'm not complaining about them. But new measurements, X-ray band, we haven't really explored fully. Tail measurements, we haven't explored fully. Multiple spacecraft would be fantastic. Having a dedicated upstream solar wind monitor would be, there's all these things that we could do that would really help us understand. And at the end of the day, Jupiter is our best local analog for extrasolar planets. right? Jupiter is the system that tells us how our own solar system was formed. It's the mini solar system within our solar system. So if we're not taking advantage of this local laboratory, then I think we're missing a trick. And there's tons of moons for the geologists. All right, so come and look at the moons too. All right, thank you for your time. Sorry for running over.
Thank you, Lisa, for your very wonderful talk, and it's a very comprehensive introduction about the the role of IO in the magnetosphere and atmosphere system, and also what Juno spacecraft has what the new findings from Juno. And is there any question from our online audience first, and then offline audience? And there is a question on the chat box. One audience said, "Why we talk about lucky Jupiter in life? Is any explanation from your talk?"
Sorry. And Jean-Noel's going to pull up the chat box maybe so we can. I didn't really understand what you said, Shengzhen.
Oh, there is a question in the chat box, but I'm not. But
Yeah.
I'm not.
Well, it says that some people, usually we say that lucky Jupiter. What does it mean? I mean, that's just a science question.
I have no idea why people say lucky Jupiter in life, but we can. I've never even heard the expression, but it's a nice one. Maybe it's because Jupiter has it all: interesting aurora, great magnetosphere, lots of moons. I don't know. Sorry.
I have a question.
Yeah.
Can your talk can you say more about Barcelona cycle and Dungji cycle?
Oh, I didn't really. I didn't mention the Vasilinas and Dungji cycles by name, did I? Right. So the Dungji cycle is, I do not like to talk about it at Jupiter. It doesn't operate at Jupiter. So Fen's really excited that you asked this question.
Dungji is British.
Because,
UK.
well, yeah. But so the Dungji cycle is when the solar wind comes in, it opens up the magnetic field on the day side, stretches back down to the night side, closes here, and then that flux circulates around again. It is the main driver of circulation within Earth's magnetosphere. It doesn't play an active role at Jupiter, and that's for a number of reasons. Magnetic reconnection on the day side is suppressed, and it's suppressed for a few different things. The rotation of the plasma, so the rotation inside the magnetopause boundary, that's too fast, that acts to suppress it. There is a large difference in plasma beta across the boundary, and that also acts to suppress magnetic reconnection on the day side. So if you actually do a map, and there have been studies about this by Adam Masters and Mariel DeRoche, and if you look at the locations on Jupiter's magnetopause boundary, which are easily able to reconnect, they're far and few between, and they tend to occur at high latitudes. And it's not even a full band at high latitudes. It's a little bit here and a little bit there. So magnetic reconnection aside, even if you were allowed or able to somehow reconnect that flux, the magnetosphere is so vast that you're looking at days of travel before the flux that's open here would be able to go and extend back. Jupiter's magnetotail extends back to the orbit of Saturn. It is a gigantic magnetotail. So somehow those solar wind lines that if they were able to open, finding themselves later on to reconnect again, or finding a different line that had been open to reconnect, it's just not it's hard to imagine that is happening at Jupiter. The Vasilinas cycle is what describes the circulation of plasma in the system. And so that's saying that the plasma from Io is moving out, it circulates around the system, and then it is eventually lost down tail. And that circulation cell is alive and active. And then you end up with loss of plasma, because as it's moving around and it gets to the tail region, that internal plasma to the system, you end up with ballooning instabilities, fire hose instabilities that stretch the field out, and it can reconnect and you lose blobs of plasma down the magnetotail. And there is an X line associated with that. And they've been able to find the Vasalinus cycle X line in data from Galileo and Juno. So this auroral process here that I was talking about is occurring. So hold on. It's occurring, you know, in these regions here. And I don't have a good Vasalinus slide. I had it in the backups, but I don't know how to access them. And I'm not sure I included these. But that is the big thing that describes the circulation. So thank you for mentioning it. All right. Tian Shu has asked, Tian Shu has asked, if one is to select the most important finding of Juno, what would be your personal preference? Oh, Tian Shu, that's not an easy question. I don't think I can pick one. The auroral acceleration was the one that I was most excited about, but that's quite different from saying it's the most important. I think just the prevalence of waves everywhere. There are just waves everywhere in the system, which isn't a surprise if you think about it, but the fact that Juno's been able to see them at all different latitudes and locations has been really game-changing for what the community needs to consider. Okay, is it okay if I take the question in the room now? The question. Yeah, go on. You've been so patient.
Can you go back to the figure that contains the velocity with the radiance?
It'll get there. It's okay.
Yes, I think it looks so kind of similar to how the dark matter was discovered. So I'm just thinking that is it any possibility that this velocity could be affected by?
So let me flip that and be a bit rude to astrophysicists and say that magnetic fields are not often discussed in astrophysics.
Constant jokes.
Yeah. Sorry. Are you an astrophysicist? Okay, sorry.
We always ask the same question.
Yeah,
what about magnetic fields?
What about magnetic fields? And so the thing is, so I heard anyhow. The point is, this effect happens because there's a magnetic field, and that magnetic field can carry electrical currents, and those electrical currents can, especially when they're perpendicular to the field, can they are associated with a force that accelerates things. So one thing that's ignored a lot with dark matter and these other things is the magnetic fields that are present in a galaxy. And so if there's a large scale galactic magnetic field and there's plasma that we're not seeing, you could expect there to be some forces associated with that. So I don't think this is evidence for dark matter. I would flip it and say this is evidence that maybe magnetic fields on a large scale should be considered a bit more when people talk about dark matter to remove the effect that they would have, and then maybe scale down some estimates. But it's a really good question, and there have been big talks about it at meetings. Yeah.
Well, I mean, like just comment on that.
Yes.
Because if you think about, so in terms of the rotational curve of the galaxy, actually the evidence comes from things which would not really be interacting with the magnetic field, right? So I think it's
Dust and whatnot.
no, actually just from the stars.
Okay.
How they move around the galaxy. And neutral hydrogen, actually, that's where it originally comes from. And so I think we know quite well that, magnetic field are important for many phenomena, but I think for the rotation curve, I think it's not. Can I? Sorry.
No, I just like, sorry, I just want to say something with the dark matter thing. And of course, also like other evidence for dark matter that's not just rotation from galaxies. So you also have gravitational like lensing and stuff like this. So it's also like there's other things also there. And there's like even more like the problem is also usually for magnetic field, you need some matter to be present, right? But if you basically had nothing, even like nothing that you can see to generate a magnetic field, it's also like suspicious, right? So there's like other stuff also, but like it's also a good observation. I think that it's like similarities, because again, I think there's something else to accelerate, the acceleration there that you would not expect. And of course, the magnetic field, that's like a very obvious calculus.
So I have a couple of questions. You mentioned I guess in terms of the heating, that this is an important process, but I think you're focusing on primarily on the upper atmosphere.
Yes.
So for the overall budget, I'm assuming the heating you're talking about is still not a significant fraction of the overall budget for.
Yeah, I think that's correct. But for the upper atmosphere thermospheric temperatures, this is what we measure with the H3 plus, it should be a significant component.
My other question is, so in this system, obviously, as you mentioned, right, that an important factor is the fact that you have IO, which is ejecting all this plasma out into the environment. I was wondering about Saturn, because in that case, you don't have that process going on.
Yeah, so you have the moon Enceladus, which is putting out a lot of material, and it puts out quite a bit less. The estimates are 50 to 300 kilograms per second of water-based material. But the difference,
that's mostly neutral.
That is neutral. And well, this is neutral too. That's 1,000 kilograms per second, and then it's ionized. So the difference though, the reason why Io affects Jupiter's magnetosphere much more than Enceladus affects Saturn, and Enceladus affects Saturn's magnetosphere quite a lot, is their locations within the magnetosphere. So Enceladus is sitting at 4 planetary radii, and the difference between the Keplerian velocity and the almost the same 10-hour rotation period there, it's smaller. So charge exchange isn't as efficient. So what happens is the material coming out extends and forms this vast neutral torus of water group particles, not ions, but they're not efficiently ionized until you get out to 6, 8. There's a little bit of there's more photoionization there, and there is electron impact, but it doesn't kick off until in the outer magnetosphere. So, so it plays a role. You still have to couple all that material once it is ionized to Saturn's atmosphere and to the planet itself. But it's a smaller system. The magnetic field is weaker. The ionization is weaker. And so it ends up being much more of a hybrid between Earth and Jupiter in terms of how it behaves.
But it does have pretty spectacular aurora.
It does, but sometimes they do turn off. Saturn's aurora sometimes turns off, and you can find evidence of that. And the moon footprints that we see all the time at Jupiter, they've only been seen 3 times at Saturn. So there's just not that signature because there's no, the plasma isn't present. So in the same levels, yeah.
I have a comment on your request of sending multiple spacecraft to Jupiter.
Oh, sorry.
Personal opinion.
You still want to do it
So
though.
expensive.
So it's not expensive. It's Then sent 5 spacecraft to the magnetosphere.
Yeah.
But nothing solved.
Oh, everything.
So
NASA made the conclusion, Siemens have solved everything. That's not the conclusion, by the way, official.
But you got 2, and then you require 3 and 4. Eventually, you will require request. It's an iterative problem, and you get 1,000.
So I think the physics that I would think more of a cluster than a Themis, right? Well, okay, the stuff I did with cluster was more at the high latitudes and the auroral stuff, but really with cluster, they were able to send the 4 spacecraft through and say, here's the extent of the acceleration region. Here's how things are changing. I don't really personally care if they find the reconnection site, although I guess that's more MMS. It would be nice, but
that also didn't solve anything.
No, but it's just something that can try and back out spatial and temporal would be helpful. Then doesn't have to solve everything. It just has to help.
NASA made
Now this is
conclusion.
I
Okay.
didn't even read the answer. This is
Yeah, I can send you, so official. So,
all right. Any more questions in or outside the room?
So my question may not directly related to this talk. So what you mentioned that 95 moon,
Yeah.
on the Jupiter. We only familiar with the 4 big one. So what about the others? Others are very small. They are off the ice, no solid. the moon?
Yeah, so I'm not sure of the properties of all of them, because that's 91 moons.
Yeah.
And I normally only deal with 4, but some of them are captured. Some of them are just small bits of rock. I'm sure some are rock, some are ice, some are captured, some are former asteroids. But they don't play a large role in the system physics.
Capture from the auroral belt? Yeah.
They could be captured from the asteroid belt or captured, yeah.
Okay.
Well,
Uh,
not, yeah.
Or at some point in the previous history of the solar system.
So what's the color of the Jupiter? That's also nickel, the metal and nickel, the color. Yeah.
The core, oh,
Or, well, actually, when someone asked about Juno, I was gonna say, if it's not about the aurora, actually, I would think, actually, the most important question is the most
internal
important question is
structure.
about the internal structure, yeah.
Yeah, I haven't followed up with what they've found, right? But
Well-
they were gonna look at the moment of inertia and.
No, it's not even just a moment of inertia, they actually get all of the gravitational
Yeah.
moments down to some ridiculous number.
Okay.
But the core is probably still hydrogen.
No,
No, they
No,
make it
Core,
rocky.
so the core, actually, all the giant planets, the core has to be solid. And it's a mixture of rocks and ice.
Not metal like the.
There is metal, but
Yeah.
probably just kind of similar to terrestrial planets.
But bigger, right?
But
like
well, so much
30 Earth
much
mass
bigger,
or
something like
something.
10 Earth mass of solid material. But one of the important results from Juno is that it actually found that core is not just like a single solid core, but that it's actually much more diffuse in the interaction between so there's kind of this very extended region where the solid and the gas is actually mixed up.
So no liquid core, all of the magnified.
It's,
Well, the outer layer is.
It's near the surface,
Yeah.
so it's 0.8 radius. Yeah, so it's quite near the surface, there's a liquid layer.
But
So it's not in the core.
Yeah, for the magnetic field.
Its pressure is very, very high, so even outside is enough to make the liquid.
But for the magnetic field, the interesting thing is that the hydrogen in Jupiter actually feels like metal, which is why it can't have that.
and they can look at changes over time with wind patterns and see it shifting, shearing. I think there's one behind you. Sorry, his hand was up first.
I wanted to sort of bring together this mention of the liquid hydrogen and the auroral acceleration
All right.
that you mentioned, because to the best of our knowledge, that's what's driving the magnetic field. So does that mean that eventually, with all that mass of the aurora being driven around, do we know if it's eventually going to slow down, or is it doing work on the aurora?
So it does work on the uppermost atmosphere where the electrical currents are coupling through, but the magnetic field is embedded, it is generated deeper down than that. So there shouldn't be much feedback from accelerating this torus all the way down into the interior of the planet. I mean, over large timescales, that all these planets always lose some angular momentum to their surrounding bodies, right? Earth's rotation is slowing very, very tiny amounts due to the moon and the moon gets farther away. So that process will be happening. But in terms of accelerating this plasma up, it's really the uppermost portion of the atmosphere that is having this persistent anti-gravitational force on it. So I don't expect that to affect magnetic field generation at all. That's happening deeper.
Sure, but I just I would have thought that if sort of Io was ejecting this material at this very high rate of like a ton per second, sort of eventually that mass would it sort of grow, or would it sort of
So that mass circulates. So this is the question about the Vassalinus cycle earlier. So it moves radially outwards through the magnetosphere, and it circulates around, and then eventually it's lost down tail. So it's lost, it's not lost into the planet. It's lost down here. So it's so it's basically it circles around here. And then it gets lost down here, and it's actually lost in blobs that are released down. So it's not coming into the planet itself.
Other questions?
Yeah, I was like, I had a question about the same thing with the graph that you talked about before with the waves, basically kind of like the deposition of energy into like the lower kind of like how like the energy from the aurora gets kind of like spread over the planet. How deep exactly does it go? Because like I was wondering, the deeper you go, probably the heat levels will change at some point, I guess, with like different densities and stuff.
It really stays in the thermosphere mostly. So if anything, the stratosphere is forcing up more, and then there'll be some circulation, and so that stratosphere boundary might have some effect, but it's not penetrating down too much. And you can see it, well, you can see it, some heating, because you can see it in the JWST. So some is getting down there, but it's in the form of currents. But I wouldn't expect it to go down much deeper. There's a question that says how much energy from Jupiter can play roles on Earth? Sometimes its movement might induce an earthquake. So Jupiter, no, I don't think.
It's because of the alignment.
Yeah. So it's Jupiter. I mean, Jupiter has an effect on the orbits of the planet in that if you look at the center of mass of the solar system, it's outside the radius of the sun. Because of how massive Jupiter is. So we're all orbiting around a point that's outside the sun, and the sun wiggles a bit, but it's too far away to trigger any earthquakes. I think plate tectonics. And I'm not going to talk about earthquakes in this room with all the actual experts. That's going to have a bigger role. So I think the most important thing that Jupiter can do from Earth is give us something fun to look at. And if you get binoculars out, you can watch the moons go around in the night sky. I mean, over a period of days, not over a period of minutes.
He actually caused a political earthquake in 1609. Yeah, when Galileo discovered the moon. Yeah, it's actually.
Okay, that is true. It did completely shift our whole view of science.
Yeah.
But yeah.
And of course, you can measure the X-ray emissions from Jupiter.
Yes.
So you can actually pick that also up. It's like basically, you can have a very simple one. You can measure the sun, and you can measure Jupiter because like the strongest, like the second strongest X-ray source in the sky. So
and the radio emissions too. If you set up a simple dipole antenna, you can do that, but not an earthquake.
Yes.
Okay.
Something.
Yeah, if there is no other question for online, so let's thank our speaker again, and thank you all for attending today's lecture, and look forward to seeing you at our next session. So bye.